Here's a problem about fishing. Now the terminology depends on where you fish, but let's look at it here. A 4 centimeter diameter bobber. So that's the thing that floats on the water and then your string hangs below it. Also called a cork, sometimes called a floater, I think. I grew up calling it a bobber. It gives you the mass, floats on a pond, and then there's a fishing line connecting it to a lead weight, sometimes called a sinker. And we have the density of the lead weight. And what fraction of the bobber volume is submerged, and what is the tension in that line that connects them? So let's draw this one. Bobbers are usually spheres. Part of it will be underwater, and then there'll be a line, and then the lead weight is there. And let's see, so that's about right. 4 centimeter diameter here, 3 grams. And down here, this is bigger, and it was 10 grams. And one thing to point out is this is a thin, light fishing line. So those are hints that mean thin, means we don't worry about the volume it's taking up. And then light means we don't worry about its weight. So just words to look for in a problem. All right, so we know the bobber is going to partially sink because we need some buoyant force to hold all this together. So that's what we have to figure out. This is yet another problem where we are thinking about forces and fluid mechanics, and that usually happens when you're thinking about buoyant forces. So the key to this problem, like many floating type problems, is to realize it is static. So we're doing a statics problem in the y. So we want to think about positive y like that. And you kind of have two choices on how to approach this. You can treat this all as just one mass, as one object, and think of the forces up and down, and they have to balance to 0. Or you can do this object and then separately do this object and keep both of those static. And it doesn't matter which one you do, they're basically the same thing. So we're going to start by thinking of it as just one big object. So let's think about the free body diagram. If we just think of it as one thing, what forces are on it? There's of course the total weight, I'll call it big mg down, if we add those two weights. Gravity's pulling on all that. And there is a total buoyant force up. And that's it. So the advantage of doing it this way is you don't have to think about the tension in the string yet, because that's an internal force. It's being applied both to this one and to this one, equal and opposite, cancel, internal force, doesn't matter. This is the sum of the external forces that we care about. Okay, so we need to sum these and make it be equal to 0. So this seems too easy here, but the reason it's going to be hard is there's 2 terms in the weight and there's 2 terms in the buoyant force. Right? There's a buoyant force due to that volume displaced, that volume displaced. So really treating it as one object isn't some huge advantage. Let's start down here just to save a little room. Let's see, so let's do the weights. The weights are down, so well, I guess I should call it MB and M lead, we'll say L. All right, so we have minus mb times g minus ml times g. There's the forces pulling it down. And now we do the forces up, the buoyant force. So the buoyant force is always the weight of the fluid displaced. So it's always the density of the water, density of the fluid, times the volume displaced. So we actually have 2 volumes displaced here. We have the volume of the lead weight, and it's the total volume of the total lead weight because it's completely submerged, plus the volume of the bobber, and I'm going to do a double subscript on you here, sub V of the bobber. Oh, let me just really get down here, S-U-B. The volume of the bobber that is submerged. Not the full volume of the bobber submerged, because what we're looking for is the fraction of its volume submerged. Once we know how much is submerged and we know the total volume, then we'll get the fraction. But we have to finish writing this. Let's see, it's the density times the volume. That's the mass of the water displaced, but now we need times g. Right. That string of forces has to be 0 because it's static. That's the idea. Buoyant force problems are often static problems. Okay, so we look at that, and right off the bat, what could we do with that? I would probably cancel G immediately. Right? So they all have G, and it's equal to 0. Every term just divide by G. So the G's are gone. And then it's really just the sum of the masses. So you could write it like this. Mass of the bobber plus the mass of the weight, like that. Just the negative of those two. Plus the density of water. We know that's 1,000. That's not too bad. Now we need the volume of the lead weight, which we weren't given, but we do have its mass and its density. So that's why we reminded you the density of lead there is that it's the mass over the density is the volume. Yes, that is correct. The mass over the density is the volume. So we would say ml over rho L. Yeah. And now the volume of the bobber submerged, we're just going to leave that as a variable because we don't know. We're not putting the volume of the bobber there, remember. Why aren't we putting the volume of the bobber there? Because it's not the full volume, it's just the submerged part. Once we have that number, that's what we're looking for. So you set that up, and that's actually, you're done. I mean, you know all these numbers. So I guess it'll be annoying, but we'll convert this to MKS units. So this is minus, well, we can just add those real quick. 3 plus 10 is 13 grams. We got to go to kilograms. So not writing units, all MKS. Plus the density of water is 1,000. Right, times, let's see, the mass of the lead weight in kilograms, 0.01, 0.01, over the density of lead in kilograms, that must be 11,300 in kilograms per meter cubed. Right, plus this thing we're looking for equals 0. So you go through and run these numbers here, and I don't know, I wrote it out kind of differently the way I set it up. I actually found one of the volumes, etc. But if you do it, you're going to get that the volume, this is submerged. The volume of the bobber submerged is 12.1 centimeters cubed. And if you really run this number, you'll get something very small because this is giving it to you, or if you solve this equation, you get a very small number because that's in meters cubed. But here I went ahead and converted to centimeters cubed. So a factor of 10 to the 6 different there. Okay, so now we have the volume of the bobber that is submerged. We were asked what fraction of the bobber volume is submerged. Okay, well then the fraction, all we do is we take our 12.1 over the volume of the bobber. And now we're going to break from MKS just for a second because I wrote this to make it look nice in centimeters cubed. Well, we can put this volume in centimeters cubed. It's just the volume of a sphere with a radius of 2. So 4/3 pi 2 cubed. Volume of a sphere, 4/3 pi r cubed. So you do that and you get, that's like 33.5, and you get 0.36. Right, so 36% of the bobber's volume is submerged, which is pretty much what I drew there. Okay, so that's the first part. And now what is the tension in the string? So now we skipped thinking about tension. We did it as one object, but now, now we're going to go back and actually find the tension. But it's not so hard because we've already done the big problem. So since we've done the big problem, we can sit there and we can get the tension from either one of these. We can solve the motion of this not moving, or we can solve the static case of this not moving. This one's a little easier because we don't have to deal with the fraction of the volume submerged or whatever. So to get the tension, we just say here it is the weight, and here is its mg, the mass of the lead g. Here is just its buoyant force, and the tension is pulling it up. Right? So we say the tension we're looking for plus its buoyant force, which we kind of already figured out. I guess I didn't give you a number for it. Where was it? It was here. It was the density of water times the volume of this thing, which was the mass of the lead over the density of lead, times, oh my god, I forgot this G. No, I canceled that G. Yeah. Times G. Alright, so those are all just numbers we know now. And then we have the minus the lead, the mass of the lead times G. So those are all 0. And we can't just cancel the G's now because tension doesn't depend on G. So suddenly we have to actually deal with those. And we could say, well, then tension is, we can start putting in numbers now. The lead was 0.01 times 9.8. And now that became positive, it's going to become negative minus, the density of water is 1,000. The density of lead was 11,300. Yeah. That's over that. The mass of the lead again is 0.01 times 9.8. So you subtract those two terms and you get a number in MKS units for the tension of 0.089 newtons. So this was a buoyant force problem with a complex object. Multiple parts, multiple densities, some things in water, some things floating on water, some tension, lots of stuff to think about. So that's sort of a complicated buoyant force problem.